All right. So now we are going to talk about life in 3 dimensions, or at least math in 3 dimensions. All right, a little bit of 3-dimensional geometry to start us off with. Now, it's usually in Calculus 3 when you start thinking 3-dimensionally when it comes to math. Until now, almost everything that we did either existed along a line or on a plane, geometrically at least. Now we're in 3 dimensions where we're bringing in the z version. So we have x, y, z as the 3 coordinates. All right. All right, so here we've got not only the x and the y-axis to form 2-dimensional plane, but then we have the z-axis. So just understand, though, that each of these axes are just copies of the real number line at 90-degree angles in 3 dimensions. Our coordinate system follows the right-hand rule, which basically says is that you take your right hand, and by the way, I have had an amputee in one of my classes that was really bizarre, who didn't have a right hand. Sorry, it was just, I had to kind of coach him through it at least. You got to kind of do a weird left-handed sort of thing, kind of think back to me. Anyway. So you take your right hand, point your fingers in the direction of the x-axis, positive x-axis, and then curl them in the direction of the y-axis, and then your thumb on your right hand will point in the direction of the positive z-axis. This will be important when we are combining 3-dimensional vectors by using what we call a cross product. All right. So, just like the 2-dimensional plane was divided into quadrants, the 3-dimensional x, y, z system is divided into octants. And of course, the prefix oct implies that there are 8 distinct regions. So octant 1, of course, is reserved for where x, y, z coordinates are positive right here. And then it kind of goes around this way, kind of counterclockwise above the z-axis. And then you get below the z-axis where you go counterclockwise again to get the 5th, 6th, 7th, and 8th octaves. But you have to really try to visualize this. The way I visualize this is that the x-axis in the positive direction is coming straight out this way. And here's the positive y-axis, and here's the positive z-axis. All right, so how we find a point, the coordinates of a point in 3 dimensions, is really analogous to how we do it in 2 dimensions. We just go, so many units in the positive x directions, and so many units in the positive y direction, and so many units in the positive z direction. That is if x, y, and z are positive. If x is a negative coordinate, then you go in the negative x direction, negative y direction, negative z direction, as appropriate. So if you have 1, 2, 3 as your coordinates, x equals 1, y equals 2, z equals 3, you go out 1 along the x-axis over 2, up 3, for example. The last coordinate being the z coordinate. Is this in your way? So, for example, the point with coordinate 3, 4, 5 is this one right out here, where you go 3 units this way, and then 4 units in the positive y direction, and then 5 units up. The z coordinate being 0 means that you're on the xy plane. When z is negative, when this number here is negative, that means that you're below the z plane. You can kind of think about this point, 3, 4, 5, as being the coordinates of the point that's at the opposite vertex or corner of a rectangular box, where the other corner, the opposite corner, in the diagonal sense is at the origin. We call this the rectangular three-dimensional coordinate system. Or if you have the point with coordinates -2, -3, 5, well, we locate that by going 2 units back this way in the negative x direction, and then 3 units in the negative y direction, and then 5 units up. You can write the equation of a plane, at least a coordinate, a plane that is parallel with the coordinate plane, by letting a variable be equal to some constant, like x equals 2, is going to be a plane that's parallel with the yz plane, but 2 units out on the positive x direction. Or here's y equals 4. It's a plane that is parallel with the xz plane. Or z equals 3 is a plane that's parallel with the xy plane, for example. And of course, we're going to deal a lot with other sorts of planes that go at any other sort of angle as well. But those are simple planes parallel with coordinate planes. So if I wanted to come up with the equation of a plane that's parallel to the xz plane, that passes through the point 2, -3, 7. Okay, so xz plane, all right, that's the plane that goes through the z-axis and the x-axis, and where y equals 0. But the point is at 2, -3, 7. The y coordinate being negative, or the y-intercept being at -3. So that means that the equation of the plane is y equals -3. The collection of points on the plane, or in space, I should say, that have y coordinate of -3, regardless of x and z. So y equals -3 would be the equation of that plane that's parallel to the xz plane that goes through that point. And if I flip through the slide too quickly and you want me to go back, let me know, okay? Make some noise. All right, now in 3 dimensions, the sort of operations that we do are quite analogous as to what we did in 2 dimensions. We can calculate the distance between 2 points by using a distance formula, but the 3-dimensional version of the distance formula, where we have the square root of the sum of the squares of the differences between the x and the y and the z coordinates. So suppose that we've got a point P with coordinates x1, y1, z1, and a point Q with coordinates x2, y2, z2, and you want to find the distance between those 2 points. It's the distance formula that you know and love back from algebra class. No surprises there. The derivation of that formula is pretty simple, right? So, for example, if you want to just focus on the xy plane, well, here's this point R, which is basically at a point that is projected from Q down to the plane that's parallel with the xy plane, but goes through this point P. And then you find the two-dimensional distance between point P and point R. And then you find the distance between these 2 points here. So it's pretty straightforward derivation of the distance formula. I'll let you look at it in the textbook. All right, the coordinates of the point midway between the 2 points is basically the average of the coordinates for the 2 points. So we have point P, point Q, the point that's midway in between. If you take a line segment in 3 dimensions that go directly from point P to point Q, then this midway point is given by just the coordinates that are averages of the x, y, and z coordinates respectively. All right. So there's the distance formula. All right. So you'll have the chance to do some calculations in your homework to do that. By the way, we can talk about spheres now. A sphere is basically a 3-dimensional surface, collection of all the points in 3 dimensions that are a fixed distance away from the point. So suppose that we've got some point in space with the center at coordinates A, B, and C, meaning the x coordinate is A, the y coordinate is B, the z coordinate is C. So A comma B comma C are the coordinates of the center. Then we want to talk about the collection of points that are distance r away in 3 dimensions from that center. Then here's the equation. Just like the equation of a circle would be like what you see there. Okay? So the 3-dimensional analog, where you bring in the z part. But if you want the 3-dimensional ball, the solid ball that is centered at ABC, the radius r, then you can, instead of having an equation, you can have the inequality, the less than or equal to r squared. So here's kind of a picture of the sphere slash ball centered at ABC with radius r. All right, let's do a quick example. Number 3. Example number 3 on page 794. So suppose that we have point P, which is at 1, -2, 5, and a point Q, which is at 3, 4, -6. Find an equation of the sphere for which the line segment PQ is a diameter. Okay, so we might have a point P here and a point Q here. And so then imagine that you've got this sphere. It looks more like a lump, I know, but So we've got this sphere, and P and Q are at opposite ends of a diameter. And of course, that diameter goes through the center. All right, so we need a point for it to be the midpoint. We need to find the radius. So let's first of all find the distance between P and Q. So distance formula, now 3 minus 1 is 2, so we have 2 squared plus 4 minus negative 2, which is 6 squared, plus negative 6 minus 5 is negative 11 squared. So we're talking about with the square root of 4 plus 36 plus 121. So 40 plus 121 is 161. Okay. So the distance between P and Q is a square root of 161. That's the diameter of the sphere then. So that means that the radius of this sphere is square root of 161 divided by 2. Let's find the midpoint. Why? Well, because the midpoint then is going to be the center of the sphere. So the average of the x-coordinate is going to be 1 plus 3 over 2. 1 plus 3 is 4, divided by 2 is 2. The average of the y-coordinates, negative 2 plus 4 is 2, divided by 2 is 1. And then for the z-coordinate, 5 plus negative 6 is negative 1, divided by 2. So there are the coordinates of the midpoint. And then to find the equation, we have x minus the x-coordinate of the center, which is 2, squared, plus y minus the y-coordinate of the center, which is 1, squared, plus z minus negative 1/2, so we'll write z plus 1/2 squared is equal to the radius squared. So the square root of 161 over 2 squared, so that'd be 161 over 4. Okay. All right. Any questions on this example? Don't worry, I'll post these slides with the ink annotation to Blackboard if you don't capture all the notes in class. All right, let's now go in the opposite direction. Suppose that we're given an equation in algebra, an algebraic equation, x squared plus y squared plus z squared minus 2x plus 6y minus 8z is equal to negative 1. And we need to identify the center and the radius of the sphere that this equation describes. So we need to put this equation in the form of x minus a squared plus y minus b squared plus z minus c squared is equal to r squared. Let's put it in that form here. So that means that we need to get the x's together. We have x squared minus 2x, and we'll just leave an open spot there, a plus something, and then plus a y squared plus a 6y plus a space that I'll leave there, and then plus z squared minus 8z, and then I'll skip some space and leave my negative 1 on the right hand side. And of course, do you remember how to complete the square, folks? You complete the square by looking at the linear term, looking at the coefficient of the linear term, provided that the leading coefficient is 1. If the leading coefficient is something other than 1, then you factor that out from both of the terms of the same variable. But leading coefficients are 1, all of these. All right, so you look at the -2 there, the linear term coefficient. Take half of that number, which is -1 for this one, and then square it. Just 1. And that's what you'll add in order to complete the square. So if you're going to add 1 there, that means we need to add a 1 there to the right-hand side. Now, what do we add to complete the square for the y's? 9, exactly. And for the z's? Plus 16. All right, plus 16. All right, so now we can factor each one of these expressions. So for the x's, we have x minus 1 squared plus then y plus 3 squared plus z minus 4 squared. And what goes on the right-hand side here? Yep, 27.
It should be 25.
25? Yeah, it's 25. Yep. So, okay, so this is a sphere that is centered at 1, -3, 4, and the radius is going to be the square root of 25, which is 5. Right. Hopefully, this is not brand new to you. You saw this stuff from an algebra class in 2 dimensions, right? This is just a higher dimensional version of what you did with circles. Any questions on this example here? All right, moving along here. Now, vectors. We know in 2 dimensions from section 12.1 that a vector is a mathematical object, but that is used in engineering and physics and other settings, that has basically 2 virtues, right? It has a direction and a magnitude, right? And there are all kinds of vector value quantities out there, like velocity, acceleration, etc. Well, if you understand the material from section 12.1, then 12.2, we're talking about 3-dimensional vectors, where you have a position vector that you might see in this form, v1, v2, v3, for example, which could be the vector that goes from the origin out to the point v1, v2, v3, for example. And any other vector that is in the same direction and has the same magnitude is essentially the same vector. Same direction, same magnitude, it's really the same vector. Here we have vector r to s. So the length of the arrow indicates the magnitude. The direction of the arrow, of course, indicates the direction of the action taking place. All right. The same discussion as we have from 12.1 applies as to how do you write the component form of a vector that goes from point P to point Q. If you know the coordinates of those 2 points, it would just be the differences between the x, y, and z coordinates respectively. So the vector PQ will be what? X2 minus x1, comma, y2 minus y1, comma, z2 minus z1, comma. Using those angle brackets if you want it in component form. Okay. Now, the same sort of operations that you do on vectors, as we did from 12.1, also apply here. You can multiply a vector v by some scalar c. Everybody understand the difference between a scalar and a vector, right? A scalar is just basically a scaling factor. It's just essentially just a real number versus vector. You can generically think about C as being the vector. Notice that it's not boldface. Versus vector V, which on the screen, when it's typeset, it'll be boldface. So you can see here CV. C is the scalar, V is the vector. Now when C is positive, the resulting vector CV will still be pointing in the direction of vector V. If C is a negative number, the resulting vector will still be parallel to V, just pointing in the opposite direction. Of course, what do you get when C is 0? Well, you get the 0 vector, right? What is the direction of the 0 vector? There's no direction. And what's the magnitude? 0. But it's still a vector. It's just a very, very special vector, right? All right. So you can multiply a vector times a scalar. The resulting vector will be parallel. You can combine two vectors. Let's take a look, example 5a. We can, here's a specific example where you have a vector u with the components of 2, -4, 1. Here's vector u, that's the black vector here. And if you multiply by the scalar 2, then geometrically that just results in a vector that's twice as long. Points in the same direction, but it's twice as long. And the components of the vector 2u will be the components of vector u, but multiplied by 2. 2 times 2 is 4. 2 times -4 is -8. 2 times 1 is 2. That's how you take a scalar multiple of a vector. Algebraically, it's just to multiply the components by that scalar. Or if you take vector v here would have components 3, 0, -1, and multiply by the scalar -2. Well, that resulting vector points in the opposite direction twice as long. And look at the components of -2v. It's just the components of vector v multiplied by -2. If we wanted to combine a couple of vectors by adding, we could do that as well. Suppose that we have vector u, which is 2, -4, 1, and we have a vector v. Remember vector v had coordinates or components of 3, 0, -1, and you then wanted to know what was u plus 2v. Well, there's u, there's 2v, and then you can use triangle rule or the parallelogram rule to geometrically add the two vectors by, completing the parallelogram that's created by putting the tails of the two vectors, and then the resulting sum of the two vectors will go from that common tail out to the opposite corner, geometrically at least. Now, how you can actually do the computation of the components of the sum is you just basically add the components of u plus 2v 2 plus 6 is 8. Negative 4 plus 0 is negative 4. 1 plus negative 2 is negative 1. Just add the components of the vectors that you're multiplying, or adding, I mean. Okay. All right. Computing the magnitude. Sometimes they call it the length, but I'll call it the magnitude of a three-dimensional vector. Basically uses the distance formula. So if you have vector PQ, the vector that goes from P to Q, vector P has coordinates x1, y1, z1, and vector Q has coordinates x2, y2, z2. Well, hey, use the distance rule. Magnitude of the vector is the same as the distance formula. No surprises there. By the way, in some textbooks, you'll see just your vector being surrounded by a single vertical line that you see here. In other textbooks, you'll see it as two vertical lines like this. Means the same thing. Okay. This will not be the last time where you might see different notation meaning the same thing. It just means magnitude. So magnitude of a vector basically is just basically the square root of the sum of the square roots of components of the vector. Do you remember I hat, J hat from section 12.1? I hat was a unit vector that points in one unit in the positive x direction. We use hat to indicate a unit vector. J hat is the unit vector that points in the positive y direction. Now we have k hat, which is the unit vector that points one unit in the positive z direction. I hat, j hat, k hat. So we can then take any three-dimensional vector and express that as a linear combination of I hat, j hat, k hat. So if we have vector v with components v1, v2, v3, we could also write that as v1 I hat plus v2 j hat plus v3 k hat. I hat, j hat, k hat, those are vectors, so they'll be boldface on the page. But in our handwriting, we'll express them as hats. So I hat might look something like that, and j hat might look something like that. K hat might look something like that, with little hats over the top. The hats, again, indicate their unit vectors. Any questions so far? Now, if you've already taken at least one semester of a physics course, then you are already familiar with I hat, j hat, k hat. But some of you have not yet taken physics, and that's fine. So, but I'm not going to go too deep into the sort of lecture that you'd expect in the physics class. All right, you'll have plenty of time for that discussion. We're just going to kind of scratch the surface with vectors, at least in the physical sense. All right, so let's take a look at example 6 on page 797. So we have 2 points. We have a point P with coordinate 5, 3, 1, and point Q, which is negative 7, 8, 1. All right, so we've got a couple of parts that we need to address here. Let's come up with the vector PQ. Now PQ the vector that goes from P to Q, you just take the coordinates values from Q minus their respective coordinate values from P. -7 minus 5, which is -12, comma. 8 minus 3 is 5, comma. 1 minus 1 is 0. So, actually, I don't even need a semicolon here, because I'm just going to say that this is equal to -12I hat plus 5J hat. Now, it's up to you whether you want to put in a 0K hat here or just leave it off. In some instances, you want to have the 0K hat for completeness. Other contexts, it's okay for you to leave it off. But to indicate that we're working in 3 dimensions here, sometimes it's better just to leave the 0K hat in there for completeness. All right, now part B of this problem, find the magnitude of PQ. So the magnitude of PQ, all right, using the distance formula, square root of sum of the squares of the magnitudes, -12 squared plus 5 squared plus 0 squared. So that's going to be 13. No surprises. So the length of that vector is 13 units. Now, the thing about a vector is that you can always come up with a new vector that's parallel to your existing vector, but out to a specified direction, or a specified length, I mean. The direction is indicated by the relationship of the magnitudes and signs of the components to each other. But if you want a vector that is parallel to PQ, but of a different length, then what you do is you take PQ and divide by its magnitude, so that you'll have a unit vector in the direction of PQ, and then we can multiply by whatever your desired magnitude is. So let's take PQ divided by its magnitude, but it basically means we take the components of PQ divided by 13. So -12 13ths, comma, 5 13ths, comma, 0. So there's a unit vector in the direction of PQ. And then you can multiply by the scalar 10. For example, if you want a vector of magnitude 10 in the direction of PQ, so we have number 10, the scalar 10, times the components of our unit vector here. So we'll have what, -120 over 13, comma, 50 over 13, comma, 0. So this vector right here has a magnitude of 10 and points in the direction of PQ. All right, just like we did with the canoe problem from section 12.1, we can take vectors and use them to analyze motion in 3 dimensions. So, for example, we have this plane flying through the air, and let's just suppose for this example that this plane is flying at 300 knots north. Now we can indicate north by the positive y direction here. So we have this direction of true north. So you see the blue vector here. There's the velocity vector for the plane. At least that's the direction of the nose of the plane, right? But then we have a crosswind. A crosswind creeps up that's going to the southeast with a magnitude of 40 miles an hour. Now, you could actually draw that vector right here. That has a magnitude of 40, and this angle right here is 135 degrees with respect to the positive y-axis. So if you were to take sine and cosine of 135 degrees, now, and that you'll have what be careful about this, is that we know that the cosine as well as the sine of 45 degrees is square root of 2 over 2. But we just got to make sure that we have our signs correct. Now, it's going to be pointing in the positive x direction, but pointing in the negative y direction, this vector right here. So that's why we have the positive piece for the I hat and the negative piece for the j hat piece. Okay. So the vector for the crosswind can be written like this, where the 20 square root of 2 comes from taking the 40 times the square root of 2 over 2. That's where the 20 root 2 comes from. And then we have a downdraft of 30 knots, which means that we have this force, or this motion, I should say, at 30 knots in the negative z direction. So that's a simple vector for us to write here. And then all you need to do to get the resulting motion of the plane is just to add up those three vectors here to get the motion of the plane plus the crosswind plus the downdraft. And then you'll have the resulting vector relative to the ground. So you'd add the 300 j hat plus the 20 root 2 times the I hat minus j hat minus 30 k hat. So we have the velocity relative to the ground is equal to the velocity of the plane plus the crosswind plus the downdraft. Let's go ahead and write those vectors. We have 300 j hat for the motion of the plane plus 200, no, not 200, but 20 root 2. Now, that's I hat minus j hat, but we'll just distribute that out. I hat minus 20 root 2 j hat. And then for the downdraft, we have minus 30 k hat. Combine like terms. So we'll have the I hat first, 20 root 2 I hat plus, and then we'll combine the j hat terms, 300 minus 20 root 2 j hat, and then minus 30 k hat. So the relationship between the components of the vector will give you the direction, and if you want the speed, and then the speed will just be the magnitude of the velocity vector. So square root of 20 root 2 squared plus 300 minus 20 root 2 squared plus negative 30 squared. All right, and you can compute that just as well as I can. That works out to be approximately equal to 275 knots, or whatever the units of speed are. They use miles per hour. Typically, though, in aviation, they use knots instead. What is a knot, anyway? Anybody know what a knot is?
A nautical mile.
Yeah, nautical mile per hour, right, instead of just a ground mile per hour. Yep. Okay. All right. When we come back from break, and we'll have a 10-minute break, we're going to tackle an exercise 75 from the exercises. You'll see it on page 800 of the textbook. So let's come back in about 10 minutes. We have problem number 75. And we're going to take a look at how we could use three-dimensional vectors to sort out this sort of problem here. So here we've got some sort of grid on the XY plane, anchor points for cables. Cable, anchor point here, here, and here. Notice that the z coordinates for these 3 points is 0, 0, 0. That's why I know that the anchor points are on the XY plane. And the 3 cables are suspending this heavy block of concrete. Now my question to you would be, what is the tension in each of these 3 cables? Who are my mechanical engineering students? What is tension in a cable? What's the definition of tension? Well, one way to define it is the magnitude of the force vector along that cable. Okay? Okay. So, here I'm going to guide you through this. I'm not going to do it step by step and you watch it. You're going to actually do this. So, pull out a piece of scratch paper. Pull out a piece of scratch paper. All right. You can turn your paper in for extra credit. Just put your name on it later on. If you want to know, do I award extra credit, the answer is yes. This is how you earn extra credit. By participating in the class doing these guided exercises. All right. So here's what I want you to do on your piece of paper. I want you to somewhat try to reproduce this image. To start off with. It doesn't have to be too pretty. You may want me to blow this out, make it look bigger. See if I could do that. How's that? All right. This point right here, see my finger? This point P right here, this is point P. Write the number P right here, the letter P. This is point P to the left. This point right here is Q. And this point right here is R. The third anchor point back here. That's point R. And this point down here at the top of the cinder block is point S. Okay, so what I want you to do right now is find the vector that goes from P to S. Find the vector that goes from Q to S. And find the vector that goes from R to S. Find those three vectors. So I'll give you a minute or two to do that. Sorry, I can't annotate this, but remember this is P, this is a Q, this is R, and this is S. So find those three vectors that I mentioned. Zero, zero, negative 2 root 3. Okay, so let's see if we agree on our vectors. Now vector PS is negative 1, square root of 3, negative 2 root 3. Vector QS is components negative 1, negative root 3, and negative 2 root 3. And the vector RS two, 0, negative 2 root 3. Now, these are not vectors that go from point S upward, because we're not solving this like a physics problem. If this were a physics problem, then we would be wanting to analyze the forces on a stationary object. So we would be wanting to draw like a three-dimensional free body diagram, right? So we could add up all the vectors of the forces for the three cables together with the force of the downward force due to gravity for the cinder block, and set the sum of those four vectors equal to 0, meaning the 0 vector, and solve for the unknown quantities. We're not going to do it that way. But what we're going to do is we're going to solve an equation. And the equation that we're going to solve is this one right here. Now x is the quantity to be solved for. And here's where you are going to do your next bit of problem solving. So negative 500 k hat is the downward force vector. Is it pounds or kilograms? Kilograms, okay. Because the block weighs 500 kilograms, the negative 500 k hat is the downward force. So what I want you to do is on your pencil and paper is to add up your three vectors, PS, QS, and RS, add them up component by component, multiply by your scalar x, and then set the left-hand side equal to negative 500k. Now, how are two vectors equal? If and only if their components are equal, huh? Okay, so go forth and let's see what you get. What does x have to be in order for this equation to be true? Give it a shot. All right, so you add up the three vectors together, add them up component by component. For the x components, you have -1 plus -1 plus 2, which is 0. So you had 0 I hat plus, and now for the y component, √3 minus √3 plus 0 equals 0, okay. So plus 0 j hat, and then the z component, -2 √3 minus 2 √3 minus 2 √3 is -8 √3. -6 √3, good. Keep me honest. Good. Okay. So we have x times -8 √3 is equal to -500 k hat. So basically, you set the k hat components equal to each other. Solve for x. So x is going to be equal to the -500 divided by -6. It's not 8, but 6 √3. Let me fix that real quick. Okay. So in other words, you got 250 over 3 root 3. But is that the tension I was looking for? No, it's just the multiplier that we would have for each of the PS, QS, and RS vectors. That when you multiply PS, QS, and RS by the 250 over 3 root 3 each, that would give you the force vector needed in order to balance that cinder block. Then, so if I ask for the tension in each cable, well, look, each cable is equal length. That's why we can get away with multiplying by the same scalar for all three vectors. So if you were to take 250 over 3 root 3 times the magnitude of any one of these three vectors, because after all, they are the same length, right? They are. Then you would have the tension, meaning the magnitude of the force vector. So let's just take the RS vector, for example. The magnitude of RS, you have what? 2 squared is 4, plus 0 squared, plus negative 2 root 3 squared, which is 12. So you have square root of 16, which is 4. So you have 4 times 250, that's 1,000 over 3 root 3. What is that? That's approximately about 192.5. Now, except in the metric system, do we use kilograms or do we use newtons to express tension? Newtons, right? So that would be the tension of the cables and each cable. Does everybody understand? Okay. This is one way of solving the tension problem. Now, as you notice on problem 76, there's a similar problem, but this time they're using 4 cables instead of 3. But can you imagine that a similar strategy is used for solving the tension for each of the cables?
Looks easier.
All right. Any questions on three-dimensional vectors so far? Now we're going to talk about combining vectors by taking their dot product. There's actually 2 common ways that we can multiply 2 vectors together. 2 common ways of multiplying 2 vectors. We're going to talk about the dot product tonight. And next Thursday we'll talk about the cross product. The result of the dot product of 2 vectors will be a scalar. You combine 2 vectors to make a scalar, sometimes called the scalar product. Now, here's one way of motivating the discussion. Now, if you remember back from science class, what do you get when you exert a force on an object to displace it a certain distance? Force times distance is what? It's work, exactly. That is, though, if we are exerting the force in the direction of travel, right? But what if the force vector is at a different angle than the direction of travel? Then, yeah, we can then just take the magnitude of the force vector times the cosine of the angle between the force vector and the direction of travel. And then it's the magnitude of the force vector times cosine of the angle times the magnitude of the direction will give you the work. So basically, you just take that component of the force that's in the direction of the direction, in this case, vector. And how you do that computation is you just take the product of the magnitudes of those two vectors times the cosine of the angle between them. And that's one way of defining the dot product between two vectors. And here's how we use the notation. We use a little dot, kind of a bold-faced dot in between two vectors. The dot product of vectors u and v. One way that we can compute that dot product is if we happen to know, or we can easily find the angle between the two vectors, and then take the cosine of that angle, and then take times the product of the magnitudes of the two angles, of the two vectors, I mean, then here's how you can compute the dot product. Is u dot v the same as v dot u? Is it commutative sort of property? Yes, exactly. Because these magnitude u, magnitude v are two real numbers. So you can swap their order. So by virtue of the commutativity of the product of two real numbers, that implies the commutativity of the dot product. Okay. Now, what if u and v are parallel with each other? What would be the angle between two vectors that are pointing in the same direction? 0. What's the cosine of 0? 1. So if the two vectors are pointing in the same direction and they're parallel, then the dot product is nothing more than just the product of their magnitudes. Now, what if the angle between them is 90 degrees, so that they're perpendicular to each other? What would be the cosine of 90 degrees? 0. So the dot product of two orthogonal vectors that are orthogonal to each other, that dot product is going to be 0. Because remember how we thought about the dot product was basically the amount of one vector that's in the direction of a different vector. Imagine how much work that would get done if the force vector was right up here. 90 degrees. There wouldn't be any work done because you're not going to move the block down this way or anywhere. You're just going to pull it up. Different sort of work. Anyway. All right, so oops, sorry about that. All right. And we generally understand that the angle between the two vectors is somewhere between 0 and pi. Here's actually how we can kind of have this discussion of what the dot product looks like. U and V are pointing in the same direction, they're parallel. Then the dot product is nothing more than the product of the magnitudes. If the angle between U and V is acute, but positive, what does acute mean? So, yeah, somewhere between 0 and 90 degrees, yeah. So that means that U dot V will be some number that is going to be smaller than the product of the magnitudes, but it's going to be positive though, because we know that the cosine of some angle that is less than 90 degrees is going to be some positive number, greater than 0, less than 1. Now, of course, if the two vectors are orthogonal to each other at 90 degrees to each other, the dot product is 0. the scalar is 0, not the vector is 0, but the scalar is 0. What sort of angle is greater than 90 degrees? Obtuse. If the angle is obtuse between them, then the dot product is going to be a negative number. And if the angle is 180 degrees, or pi, radian, that means that the two vectors are parallel with each other, but pointing in the opposite direction, then the dot product will just be the negative of the product of the magnitudes. So this just here reiterates the discussion. Orthogonal products, or orthogonal vectors have a dot product of 0, or vice versa. So one way that you could tell that two vectors are orthogonal is if you take their dot product and they're 0. That's a good tool to have in your tool bag when you're doing problem solving. You need to find out two vectors are orthogonal, take their dot product, see what you get. If it's 0, then you got it. And if their dot product is not 0, that means that the two vectors are not orthogonal to each other. Orthogonal, perpendicular, 90-degree angles, whatever, same thing. We use orthogonal, though, in the context of two vectors meeting at 90 degrees. This is example number 1 at the bottom of page 802. So we've got a vector u, which is 2I hat minus 6j hat. And we've got a vector v, which is 12k hat. What is the dot product of these two vectors? Of u and v in this example here? It's going to be 0 by inspection. No computation needed, because you have one vector that's just sitting right here on the xy plane with no z component. So that means that any vector that is along the z-axis is automatically going to be orthogonal to vector u. So vector v is automatically orthogonal to vector u. So that product u dot v is 0. This second picture right here is from part B of the same problem here. For part B, we have vector u, which is root 3 comma 1. That's this one here. That's the blue vector. Well, we've got vector v right here, 0 comma 1. So two-dimensional vectors. What is their dot product? Well, magnitude u times magnitude v times the cosine of the angle between them. All right, so magnitude v is equal to 1. Magnitude u is equal to the square root of 3 plus 1 is 4. Square root of 4 is 2. And then what is cosine of pi over 3? It's 1/2, right? Okay. So u dot v is equal to magnitude u times magnitude v times cosine of the angle between them. So 1 times 2 times 1/2, that's equal to 1. Any questions on how to do it? I know that on a lot of the newer calculators, and probably any calculator that's newer than anything that I use, can do dot products of vectors, cross products, and the other sort of operations on vectors. But make sure you know how to do this by hand. All right. Now, algebraically, how you can take the dot product of two vectors is just by multiplying their components together and adding up those products. So you have vector u, and you have vector v. U is u1, u2, u3. Vector v is v1, v2, v3. While u dot v can be written as u1, v1 plus u2, v2 plus u3, v2. Now, they call it a theorem because this is derived from the definition of the dot product. Now, let's go back and review. There's the definition of the dot product. And it just so happens, though, as a theorem, that you could also write your dot product this way. And why should this be so? I'm not going to go through the proof, but I'm glad that you asked. But actually, if you're interested, you remember from trigonometry, the law of cosine? Maybe, maybe not. But it basically uses argument from the law of cosine. So, if you are, is anybody here going to be a math major, by the way? Just curious. Math major? All right. Thinking about it. So, if you are interested in working through the proof, I'd be happy to do it with you. But almost everybody else would be like passed out by the time we're done. Or wanting a stiff drink or something, I don't know. I probably would too, but just work through the proof, and but basically use the law of cosine. So for as the result of the difference of two vectors. Right? So look through. But what I do want to pay attention to, and I want you to highlight or put in your notes, look at the top of page 804. Top of page 804, there are two implications, though, that come as a result of this theorem of how we can compute the dot product. Now, if you see number one toward the top of page 804, is that if you've got two vectors, u and v, and you want to find the angle between them, then you could write cosine of theta is equal to u dot v divided by magnitude u, and here I'm trying to keep my notation consistent. Magnitude u, magnitude v. So if you want to find the angle between two vectors, then you can use this formula. Oops, that's not b, it's going to be 2. The second implication would be that one way of finding the magnitude of a vector would be to take the square root of the dot product of that vector with itself. Now, why should that be true? Now, vector u dotted with vector u will be magnitude u times magnitude u times the cosine of the angle between them. But cosine of 0 is 1. Okay, so cosine of 0 is 1. So this be 1 times 1. So that means that u dot u is the square of the magnitude of u. So take square roots of both sides. So this gives you an alternate way of finding the magnitude of a vector. It's just dot the vector with itself and take the square root. Okay. All right, let's do an example here. Number 2. We have vector u with component square root of 3, comma 1, comma 0. We have vector v with components 1, root 3, 0, and vector w with components 1, root 3, and 2 root 3. Now we're going to do some computations. Part A, let's compute u dot v. Now u dot v, that means that we take the x component of u times the x component of v. Root 3 times 1 plus the product of the y components, 1 times root 3, plus the product of the z component, 0 times 0. So we have root 3 plus root 3, which is 2 root 3. So there's u dot v, just a scalar. Find the angle between u and v. Okay? So I know that the cosine of the angle is going to be u dot v divided by magnitude u times magnitude v. Now u dot v is 2 root 3. Magnitude u, well, the square root of what? Root 3 squared plus 1 squared is going to be 2. Magnitude, and you see that the magnitude of v is also 2. So let's see here. 2's cancel. Root 3 over 2. So cosine of theta is root 3 over 2. So what is theta? What is the arc cosine of root 3 over 2? What is it? 30 degrees. 30 degrees or pi over 6. Either way, radians, degrees, it's okay. See? What's the angle between u and w? Okay. Now let's go ahead and find u dot w first. U dot w, root 3 times 1 is root 3, plus 1 times root 3, plus 0 times 2 root 3 is 0. So this is 2 root 3. Magnitude u is equal to 2. Magnitude w is equal to, what, 1 plus 3 plus 12 is 16, right? So magnitude is 4. Cosine of the angle between u and w is going to be u dot w divided by magnitude u times magnitude w. U dot w is 2 root 3 divided by magnitude u, which is 2, times magnitude w, which is 4. So 2's cancel, leaving you a square root of 3 over 4. And then to solve for theta, you just take arc cosine of square root of 3 over 4, which is fine because of the fact that theta is some angle between 0 and pi, which happens to be the range of the arc cosine function anyway. So, and I guess that works out to be about 64.3 degrees. Okay, or about 1.12 radians, right? 1.12 radians. All right. Let's talk a little bit about some properties of the dot product now. The commutative property, we already talked about that. Commutative property basically says is that you could do the operation in either direction. You can combine it in the forward direction or the backward direction. U dot V is the same thing as V dot U, just like with addition of real numbers or multiplication of real numbers. You have the associative property that basically says is that if you've got a scalar times a dot product, well, you can bring that scalar in with the first vector or with the second vector and then carry out the dot product. You have the distributive property that basically says is that you're going to take the dot product of one vector with the sum of two other vectors. But you could also write that where you take the dot product first and then add as well. So U dot V plus W would be the same thing as U dot W plus U dot V. So hopefully these are not too strange. You've seen these before from previous math classes. Even though the names of the properties might not necessarily be completely familiar, but you've seen these sorts of properties being used in the past. And look, and these equations go in either direction. So if you've got a U dot V plus a U dot W, then you can factor it to where that's the same thing as the U dot V plus W, for example. What I want to talk about right now, though, is the ideal of projection of one vector onto another. Very important, especially for physics. We're going to talk about some basic things here, though. For those of you who take physics and also engineering classes, you'll have plenty of practice with this. Now, from time to time, it's going to be important for us to find a vector that is parallel with one vector, but it's the projection of a different vector onto the one vector. So here's what we think about. Here's a way of visualizing the projection of a vector U on a vector V. Here's a way of visualizing. So you put the tails of the two vectors together right here. And imagine that vector V is horizontal. So you've got vector U up at some angle. And then imagine that you were to shine a flashlight where the beams of light go directly down. And then you imagine the shadow that's cast by the vector U onto vector V. And that shadow would be the length of the projection of U onto vector V. Here's the notation. The notation of the projection of U onto V. Make sure that you get this right. The vector that you're projecting is U onto vector V. The vector V is what you see as the little subscript down here. Now, if the angle between the two vectors is acute, then that projection is going to be parallel to vector V in the direction of vector V. But if the angle is obtuse, the resulting projection will be parallel to V but in the opposite direction. Of course, if the angle is 90 degrees, then the projection would be the zero vector. All right, so there or a couple ways that we could write the projection calculation with formulas. One way is to understand this ideal of what the scalar of the projection of u onto v, the SCAL of u onto v, which is nothing more than just take the magnitude of u times the cosine of the angle between vectors u and v, which will basically give you the magnitude of the projection vector. The magnitude or the length of the shadow vector. That would be that scaling factor. That scaling factor would be positive if the angle is acute. That scaling factor would be negative if the angle is obtuse. And with using this device of the scaling factor, we can think about the projection of u onto v as that scaling factor times the unitized v vector. Remember that you can take any vector and come up with some other vector that is parallel with that vector and make it any length that you want by unitizing the first vector and then multiplying by the scalar, which will give you the magnitude that you desire in the direction of that first vector. So if we want a vector that's parallel with the v vector and that has the length of that scaling factor, then we just take vector v divided by its magnitude times that scaling factor. Now remember what the scaling factor of u onto v is. That was magnitude u times cosine of the angle between them. So when you take that together with the v over magnitude v, then you get this calculation right here. So let's just see if this makes sense. Because think about this cosine of theta here. That's probably the missing piece here. Remember, cosine theta, you could write this as u dot v over magnitude u times magnitude v. Okay? So imagine that in this calculation right here, that the magnitude u's will cancel, and then you'll have magnitude v together with this magnitude v squared, which is the same thing as v dot v. And here's your u dot v that you see right there, and then times vector v. Right? Now, what you see in the parentheses right here is just a scalar. U dot v is a scalar, v dot v is a scalar. So u dot v over v dot v is a scalar. So you can see that the projection of u on the v is just some scalar multiple of vector v. It looks a little bit intimidating at first, but just understand it's the amount of vector u that's in the direction of v. All right, with that, let's take just a short break, 5 minutes, and we'll come back and we'll finish up section 12.3. Okay, we are continuing this discussion of the progression. We are almost done. And at the end of the class period, you'll have the opportunity to convene in your cohorts to begin preliminary discussions of your projects. So, but we're going to do some calculations of projections. And then, of course, you'll have the opportunity in homework to do many more calculations as well. Let's take a look at example 3. On page 806 of the textbook. So here we're going to, we have a vector u, which is 4, 1, and we have a vector v, which is 3, 4. And what we need to do is to calculate the scalar component of u in the direction of v, and then calculate the projection of u onto v. Okay, so first of all, the scalar component of u in the direction of v could be written as u dot v over magnitude v, because of the fact that it could also be written as magnitude u times cosine of the angle between them, which is the same thing as this calculation. Now, u dot v, well, 3 times 4, which is 12, plus 4, so yeah, 12 plus 4 divided by magnitude v. Well, 3 squared plus 4 squared is 9 plus 16 is 25. Magnitude v, therefore, will be 5. So we're talking about 16/5. So there's your scalar component of u in the direction of v. And then the projection of u onto v then could be written as 16/5 times magnitude, or times v divided by the magnitude of v. So v, of course, is 3, 4. Divided by magnitude v, which is 5. Now, one way that you could write this vector is just 16 over 25. 25. Fix that real quick. Times 3, 4. Or if you want to multiply that scalar in, that's fine too. You have 48 25ths, comma 64 25ths. So there's the projection of u onto v. One way of doing it. Otherwise, if you want to do, the u dot v over v dot v times v, then that's fine too. U dot v is 16. V dot v, that's magnitude of v squared, but magnitude of v is 5. Squared is 25 times v. So either way is perfectly fine. Here we're just using the technique of the scalar component of u in the direction of v. Good. All right. Now, oh, by the way, here's a picture of what we just did. So the red vector is u, the blue vector is v, and the black vector right here is the projection of u onto v. Notice that the projection of u onto v is parallel with v, but it's the shadow of u cast onto v. Okay? All right. For part B of this problem, if you want to compute the projection of u onto v, we can do that here. Look, here we've got vector u, we've got vector v. Vector u is -4, comma, -3. Vector v is 1, comma, -1. So if you want to compute the projection of u onto v, so that'd be u dot v over v dot v times v. U dot v is what? -4 times 1 plus 3. So -4 plus 3 is -1 over v dot v. Well, the magnitude of v is going to be square root of 2. Square root is 2. And then times vector v. So we're talking about -1/2 times vector v. And that's the projection of v onto u. So there's your projection right there. Now, notice what this looks like. V is this blue vector. U is the red vector. But notice that the projection of u onto v is a vector that points in the direction opposite of v, because of the fact that the angle between u and v is obtuse. Any questions so far about projections and how to compute them? All right. Let's talk a little bit about applications of dot products. This first one has to do with work and force. Remember that work is nothing more than force times distance, provided that the force is applied in the direction of the distance. Otherwise, it's the force vector dotted with the direction vector. Direction where the d vector gives you the direction and the distance. And if it so happens that the force vector is in the direction of the distance vector, or the direction vector, then we have the scalar definition of force. Otherwise, take the dot product, and then you'll have the amount of work. And by the way, is work a scalar quantity or a vector quantity? Yeah, work is a scalar quantity versus force, which is a vector quantity. Let's take a look at example 4. And it reads this, that a force F, where you have this force vector 3, 3, 2 in newtons, moves an object from point P to point Q. Well, here's point P right here, and here's point Q down there. So you have a point P here, a point Q here, and here's your force vector, which is the red vector here. Now, what we're going to do is calculate the d vector, which goes from P to Q. And then take the dot product with the force vector so we can calculate how much work gets done. By the way, that angle between them is 25 degrees, which you can calculate this as well. So work is going to be the force vector dotted with the PQ vector, where PQ is that vector that gives you the direction and distance of the displacement. So I think that D, I guess, stands for displacement vector, huh? So F is 3, 3, 2 dotted with the PQ vector. Now the PQ vector 6 minus 1 is 5. 6 minus 1 is 5. 0 minus 0 is 0. So take that dot product. 3 times 5 is 15. Plus 3 times 5 is 15. Plus 2 times 0 is 0. So you get 30. By the way, what are the units of work? Where force was in newtons, right? And PQ was in meters, right? So work is going to be in Newton meters, right? In other words, joules, exactly. Okay. Moving along here. This is the boat trailer problem. That's what I like to call it. Now, one way to simplify it is to think about, you have that incline up there, and you've got a block sitting on it. Now, the full acceleration of gravity is not going to propel it down the ramp. Only that component of gravity that points down the ramp is what is going to accelerate that block. And not only that, this component here, this normal component, is the weight that this ramp feels. So what we could do is we could resolve the force due to gravity into this normal component and this parallel component. I call it the boat trailer problem, because you can kind of think about it like this. So here you've got a simplified truck, and then here you've got, and I'll kind of do it at an angle here. Here's your trailer with your boat or some other object that you're hauling here. So here you've got some ramp, and you're going to back your boat down into the lake, right? What is the braking power that's needed to prevent your whole rig here from being pulled down into the lake, for example? And not only that, how much weight is being experienced by the ramp, for example? That's what we call the fishing boat problem. So what we do is we come up with the mass of the object on the ramp. In this case right here, it would just be the boat. But if the truck was also on the ramp, then you would just have to take the combined mass of the system, find the idealized coordinates of the center of the mass of the system, then, but let's just suppose it's simply the boat. And just idealize that system to where the center of mass is like right there, resting on the ramp. In this case, it's the wheel. Right? So anyway, so you have the weight of the trailer. Is weight a force? What is the difference between weight and mass?
Weight has a force included in it.
Right, it's basically the force times the acceleration. Huh?
Be mass times.
So mass times acceleration, yeah. Now, unfortunately, though, in our English system, or common system that we use here in America, we use pounds for both, right? Versus in the rest of the world, they use newtons for the weight, right? Versus what do they use for mass? Grams, etc., kilograms, whatever. Anyway, but just understand that weight is a force due to gravity. Now, what we would do is we would resolve this into a normal component and then to a parallel component that points down the ramp. So what we typically would do is to get a unit vector that points down the ramp. So just figure out what that angle is for the ramp, and then a unit vector that points down the ramp, if this is a two-dimensional system, would be cosine of theta, comma, negative sine of theta. And think about that for a minute. That would be your unit vector. And it would be a unit vector because of the fact the square root of cosine squared plus sine squared of the angle is 1. So then let's just suppose, so this is W, just call this U, or U hat I should say. And then what you do is to find the amount of braking power that you need to keep your boat from being pushed down into the water is by calculating the projection of W on to U hat. U hat. That's the braking power that you need. If you want the normal weight here, the weight that's experienced by the ramp, then what you could do is then you could take W minus U hat, or W minus the projection W on the U hat to give you this guy right here. Okay. So anyway, but that'd be more of a physics problem, huh? So I'll just leave it for a physics class for you guys to tackle those. But you might see something on the homework as well. It's not too hard to do. I just kind of outlined the basic idea. Here, let's just do a quick example of number 5 here. That kind of gives the same sort of result. Here we've got a simple block on an inclined plane. For example, number 5, we've got 10-pound block rests on a plane that is inclined at 30 degrees below the horizontal. Find the components of the gravitational force, parallel and normal. All right. So, look, we've got this weight of the block, which would be a negative 10 J hat. And then, how can we come up with a unit vector that points down the plane? The green vector here. So, now, V will be cosine 30 degrees, comma, negative sine 30 degrees. That would be V right here. This unit vector that points down the ramp. Now, cosine of 30 degrees is what? It's Square root of 3 over 2, right? And negative sine 30 degrees? It's negative 1/2, right? Now, calculate the projection of F onto V hat. So you're going to have what? F dot V divided by V dot V. Now V, remember, is a unit vector, so V dot V is going to be 1 times V hat. Now, V dot V is 1. F dot V, F, remember that F is 0, negative 10. So when we take the dot product, you'll have what? Square root of 3 over 2 times 0 plus negative 1/2 times negative 10, which is 5. So you've got 5 over 1, which is just 5, times V hat. And V hat, of course, is square root of 3 over 2, comma, negative 1/2. So the projection is going to be 5 root 3 over 2, comma, negative 5/2. And if you were to take the magnitude of this, you would just get 5, right? Because this vector right here is just 1. It's a unit vector. So the amount of force that's being applied on this block due to gravity to push it down the block is just going to be 5 pounds. Because of this right here. All right. Now, if you want to find the normal component of F, the normal component of F, which is the blue vector right here, the component that's parallel to the surface of the ramp, and that's just going to be the downward force, F, minus the projection. Minus the projection. See, I can't talk and write at the same time. So we have F as 0, negative 10, and then minus the projection, which is 5 root 3 over 2, comma, negative 5/2. So we do that subtraction, 0 minus 5 root 3 over 2, so you get negative 5 root 3 over 2, comma, negative 10 minus negative 5/2, so you get negative 10 plus 5/2. So in other words, you get negative 20/2 plus 5/2. So you get what, negative 15/2? So this vector right here is the blue vector, which is the normal component. So if you want, then you could take the magnitude of your n vector. And what is that magnitude? So basically 5 root 3 over 2 squared plus 15/2 squared. And whatever that works out to be will be the weight that's experienced by this ramp in the direction that is normal to the surface. Okay? Whatever that is. That's something you can easily calculate. All right, so that's it. So if you know how to do this problem, then you could solve the fishing boat problem. Now, the rest of the class period is for you to use constructively. I would suggest that you do a quick huddle with your cohorts either in the classroom or out in the hallway somewhere or out in the park bench out there, and get together, exchange contact information, arrange dates and times for you guys to meet so you can start looking at your project together and so forth, okay? Have a good night, and I'll see you on Thursday.